Okay, in the last lecture video, we talked about how the mass number A in a chemical symbol tells us the number of protons in an atom plus the number of neutrons. But it turns out that this mass number A also tells us the total mass of one atom. So essentially, how much it weighs. Now, what's important to remember this, is the units of this mass. So it's not measured in grams, it's not measured in pounds, which we're used to. The units of measurement, the measurement scale that's used, is atomic mass units, also known as AMUs. So this is just a different measurement scale. So it's just like how people in the United States typically measure distance in miles, whereas everybody else in the world measures distance in kilometers. We like to measure things in pounds. Everybody else uses grams and kilograms. But for the mass of an atom, it's so tiny, as we saw in one of our first videos, that if we were to measure it in pounds, we'd be writing like 26, 27 zeros every time we wrote it down. So instead, we use a measurement scale that allows us to numbers. So just to give you a sense of how they're related to one another, one atomic mass unit is the same thing as 1.7 times 10 to the minus 24 grams. So that means every time you have 1.7 times 10 to the minus 24 grams, you have the equivalent of one atomic mass unit. So just to give you a frame of reference, how much then, let's ask the question, if we had a person who weighed 130 pounds, how much would they weigh in grams? And how much would they weigh if we instead measured their weight in atomic mass units? Well, I know that if I had 1 pound, I would have 454 grams. So if I have a 130-pound person, and for every pound I have 454 grams, I could multiply these together, 454 grams for every 1 pound that I have, and that would tell me that my 130-pound person, if I were able to change my bathroom scale to measuring grams instead of pounds, that number readout would be 58,967 grams, or 59 kilograms. I kind of wish that my scale was in kilograms. Then we can take this calculation one further, and we say, okay, if that 130-pound person, that's the same thing as saying that they have a mass of 58,967 grams. And I also know now that I have one atomic mass unit for every 1.7 times 10 to the minus 24 grams. That's equal to 3.6 times 10 to the 28 atomic mass units. So that would be the same as writing 3600 ... In fact, I would have to write out a total of 27 zeros to write this number out. So just as an aside, so you don't worry about it, writing things, numbers like this, is called scientific notation, and we can convert between scientific notation and decimal notation. We'll learn how to do that later on in the semester in more detail. But right now, I'm just trying to give you an idea of magnitude. So if I was going to measure, if we were going to measure people's weight in atomic mass units, the numbers would be really big, right? That would be crazy on a bathroom scale. That's why we measure body weight in pounds or kilograms. But for atoms, measuring them in atomic mass units gives us regular numbers that we can deal with. Okay, so let's look at some examples then. Let's go back to the isotopes that we worked on earlier. Carbon 12, carbon 13, and carbon 14. So now looking at our mass numbers, we want to treat it a little bit differently. So instead of just looking at the number of protons, neutrons, and electrons that we can get from these mass numbers and atomic numbers, let's use our mass numbers instead to get the number of the mass measured in atomic mass units. So for carbon 12 then, the mass would be 12 atomic mass units. For carbon 13, it would be 13 atomic mass units. And for carbon 14, it would be 14. That's a 1. 14 atomic mass units. And again, to give you an idea of scale, if I were to convert the mass of this one carbon atom for carbon 12 from 12 AMUs to pounds, it would be 4.4 times 10 to the minus 26 pounds. So if I were to write that number out, I would have to write 0.00 dot dot dot. I would have to write a total of 25 zeros and then 4. So that's a very, very tiny number that we would have to write if we were measuring the mass of one carbon atom in pounds. But since we're measuring atomic mass units, the number is 12. So in the world, if we wanted to look at how much of the different isotopes of carbon there is, we would find out that most of the carbon in the world, in fact 98.93% of the carbon out there, is carbon 12. Then another 1.07% is actually carbon 13. So the percent that actually exists of carbon 14 is really, really tiny. Okay? But because of this, we can calculate the weighted average. So what's the average mass of a carbon atom? That takes into account the masses of all three of these. The 12 AMUs, the 13 AMUs, the 14 AMUs, and whatever else there is in very, very, very tiny abundance. So we want to know what's the average mass. So if we were to calculate, we would find that the average mass of carbon is 12.01. So sometimes you'll see the chemical symbol written like this. So this 12.01, we see it's slightly bigger than 12 because there's also a contribution to the mass of carbon coming from carbon 13 and carbon 14. But the number's closest to 12 because 98% of the carbon is 12 AMUs. So when you weight the average and you put more emphasis on the carbon that there's more of, which is carbon 12, you get an average mass that's closer to that value. So we say that the average mass of a carbon atom is 12.01 atomic mass units. If we look at this same symbol and we want to use that mass number to get protons and neutrons, we would just round it off to 12 and then use the atomic number and subtract from that 12 to get the number of neutrons.